So further part, what we have now, so this is a square, and here is so what we can do, we can just do a square root of that part. Okay, so let's go for a square root. So c by cc divided by 2m all square is equal to sorry, square is there, so we got this is equal to k by m, under root of k by m, right? Now further, C, because we actually want to find out this critical damping coefficient. So this is equal to 2m into under root of k by m, right? Further, this 2m, 2 let's keep outside. If it m is goes inside of the square root, it becomes a square. Okay, so what we have now, C is equal to 2 into under root of k into m after the simplification. So this is my equation of critical damping coefficient, right? Or even you can also derive from here, because as you know, what is the under root of k by m? What is this term? Anybody? What is this term under root of k by m? Yes. Anybody else? What is this term? Okay, that's also right. That's also right. Deflection upon g, that also right. But here I can see this is nothing but your natural frequency. Okay, so I can write this is as a 2m omega n. Okay, omega n is equal to under root of k by m, as you know, right? It's a natural frequency in radian per second. So this is your natural frequency omega n. So these are my two equation of critical damping coefficient. Okay, so I can also find the value of Cc by using this equation to under root of k into m, and I can also find from this. Okay. Yes, I will give you a time. Okay, so we'll first derive this equation. Now you can write your if you want to write, you can write now. Okay, so just note down these things. Okay, so we have started from here, because this part we already finished from equation up to the equation 3. Then we have started from here. Okay, so you just kindly write from this point. Okay. Okay, so now you can start writing. So note down this thing in your notebook and tell me once you finish this. So we'll proceed for the next part. Okay, so today we will start from here only. So this is from starting only, nothing else. damping coefficient is a C only, not E. Okay, damping coefficient is a C. Okay, this is C, capital C, this is small c, right? This is also C, not E. Okay, C for cat, not the elephant. Okay, this is also C suffix C. This is the E. Okay, it's a, this is the E. Okay, fine, done everyone. Okay, done. The students do it fast. What about other student? Got only one response. Chirag, Rishabh, Ajwal, Shivam. Okay, now all done. Fine. So now let's move further. What we have now, so this is what the critical damping, right? So here we come up with the two damping coefficient, critical damping coefficient and the damping coefficient itself, right? So if you just take a ratio, if you take just a ratio of these two, the ratio of this damping coefficient to this critical damping coefficient, it's called a damping ratio zeta. Okay, so the next definition, next term that we're going to introduce here is a damping ratio. Okay, that is called zeta. Okay, this is how we can write zeta. Okay, so damping ratio zeta is nothing but zeta is equal to C divided by Cc. It is the ratio of, or we can define it is like, it is the ratio of damping coefficient to the critical damping coefficient. Okay, it is the ratio of damping coefficient to the critical damping coefficient, that is called damping ratio zeta. Okay, so here you can see the zeta is equal to C divided by Cc. Now C is a damping coefficient. Cc is a critical. So what we have now as a critical damping coefficient? We have this equation, right? So 2m omega n. Okay, so this is nothing but the equation of this Cc here, right? So from this, what we can get here, that from this omega is going over this side. So we can write here, from this relation, C divided by 2m is equal to what we have, zeta omega n. Okay, zeta omega n. The reason of doing this is to replace this term. You can see these two terms is in our root. Okay, you can see S1 and S2. We have a C by 2m. So we just want to replace this term. We just want to replace this term K by m in terms of natural frequency, because ultimately we're going to find out the natural frequency, damn natural frequency, right? So we just replace the C by 2m with this term. Okay. So for that, what we are doing, we are nothing but use the damping ratio zeta, C by Cc. C is the as it is. Cc value that is coming from this equation 2m omega n. Now we keep this term as it is, C by 2m over this side. The omega is now goes on the left hand side. It becomes zeta omega n. Okay. So let us consider, this is the equation number 4. Previously we used up to equation 3. Okay. Same way we can also proceed for this equation. What is this? Omega n is under root of k by m. Okay. So what we can write here, omega n natural frequency, that is given here as a k by m. Okay. So from this we can write omega n square is actually k by m simply. Right. So this is, let us say, equation number 5. Use the equation 4 and 5 and put it in this equation number 2 and 3. You can see C by 2m and K by m. So we replace C by 2m with this zeta omega n, and we replace the K by m with this omega n square. Okay. So if you put that two equation 4 and 5 in the equation number 2 and 3, we'll get, so we can write here, put the above two equation 4 and 5 in equation 2 and 3. So we'll get the two roots. We'll get the two roots S1 and S2 is equal to, let's see it again. Here is a minus sign, so we can write minus zeta omega n, right? Plus sign, you can see the plus sign as it is. Here is a minus zeta omega n square minus omega n square. Okay. So this is what under root of zeta square omega n square minus omega n square. Okay. This is my S1. And if I write S1 plus or minus, it means I have S1 and S2 both. Right. So this is my two root S1 and S2 as a plus or minus. So as you can see here, the omega n is a common term, omega n here also, and you can also keep that omega n square is a common from this, and if you come out from the under root, that will give you the omega n itself. So we can keep that omega n common from this old term, and then finally what we have now, minus zeta plus or minus under root of zeta square minus 1 to here only into omega n. Right. So this is my root S1 and S2. So from this we can write S1 is equal to minus zeta plus under root of zeta square minus 1 into omega n. This is my S1. And S2 is equal to minus zeta minus under root of zeta square minus 1 into omega n. Right. So these are my two roots, S1 and S2. Okay. Right. So first write up to this of this damping ratio. Okay. So just note down up to this and then we'll proceed for the next part. quickly. Let me know once you have finished this. Okay, fine. So most of you have done this. So now these are the two roots, right? And here the solution is now based on these two roots, right? S1 and S2, right? So our final solution is in terms of the zeta, that is what damping ratio and natural frequency, right? So here, based on the zeta, we have classified the three different cases here, okay? Because the damping is the zeta is actually a ratio, and the ratio having a three possibility. The ratio must be equal to 1. The ratio is less than equal to 1 and greater than equal to 1. Right. So according to that, we have classified this under three different cases. Okay. What are those cases? If we can say if the zeta is less than 1, if the zeta is less than 1, then we consider the case is as a under damping system. It's called under damped system. Okay, zeta is less than 1 is called under damped system. See, Virendra, if we consider a zeta is 0, okay, if the zeta is 0, it is only possible. Let us think here, in which case that zeta is 0. Think about it, in which case and how it is possible. Just try to think about it. How you get that zeta 0? Just think about it and tell me. This is the equation of zeta. Look at the equation. Look at the equation. No, if you consider a CC0, it's an infinity, okay? If the term 0 as a denominator, that's give you an infinity, right? So it is only possible if you have a C equal to 0. And what do you mean by C0? If you consider a C is a 0, if you consider a C as a 0, it means what? No resistance, no damping. It is not a case of damping itself, right? So if there is a no damping, there is a no meaning of damping ratio, right? That's why we cannot consider 0. I hope you understand now, right? So 0 is never being the ratio zeta. Okay. So here zeta is less than 1. It's an underdamped case. If we consider zeta is equal to 1, this is called critical damping. It's called a critical damping system, because if you consider the zeta is equal to 1, what does it mean? If the zeta is 1, C is equal to CC. That is nothing but your critical damping case. If consider C is equal to CC, that is nothing but your critical damping coefficient, right? So C is equal to CC is the damping is called critical damping. And at last that C zeta is if it is a more than 1, which is called over damped system. Okay, so here there are three different cases. Case number 1, if the zeta is less than 1, that is under damped system. Zeta is equal to 1, it's a critical damped system, and zeta is a more than 1, that becomes over damping system, right? So this is the three different cases that we are going to study here in this case. Okay, so let's start the first one. Okay, that is what? The over damped system. Clear? So first write these three things and then we switch over to the next part. It's a over damp system. So first we discuss if the zeta is more than 1, that is over damping case. Okay, clear up to this? Any student having any doubt up to this simplification derivation? See, this is a pure mathematical formulations. So note down every step, okay, and later just try to refer this all. Just try to refer this all. Then only you can understand, you can memorize this thing. Right? These three cases is a very, very important case of this chapter. Right? It's a most IMP. Many of the students are asking me, give me some IMP, give me some IMP. This three is the most IMP, right? So kindly remember this formulations, try remember these three cases for exam point of view as well as for learning point of view. Okay, done now. So let's move to the first case, over dam system. Case number 1, over dam system. Azil, rather sharing this all document, it is better to write. Okay, so first write down these all steps. I will share later. Okay, it is better to write these things from your side by your own handwriting and in your words. That is always being better to learning rather than directly taking these notes. So here in overdam system, what we have, what is the value of zeta? As we know and discussed previously, the zeta is greater than 1. That is what the case of overdam. Okay, the zeta value more than 1. So what happened in that case? The critical damping coefficient is less than, or you can say damping coefficient is more than critical damping coefficient. C is greater than C. Remember, it's not a E, it's just a C. I'm using this marker. That's why initially it's just a dot that you can see the dot is here. So it's actually a C only. Don't consider it as E. Okay. So C greater than C. Okay. So this is the case of the overdamping system, right? And here we have two roots that we initially discussed. What should be the two root? So here in overdamp system, the roots has been given here S1 and S2, just like as S1 is equal to minus zeta plus under root of theta square minus 1 into omega n, and S2 is equal to minus zeta plus under root of theta square, sorry, here is a minus into omega n, right? Fine. Now what we have, so as you can see, the zeta value or the roots value is a depends on zeta and omega n. So in a particular case that omega n is same for the system. Now the only dependency of these roots that are on the zeta. Okay, if you consider a zeta more than 1, so here if you consider, let's say 2, 3, 4, 5, whatever the value of zeta. So if it is a more than 1, so let us consider here zeta is a 2, for example. Okay, so 2 square is 4, 4 minus 1 is 3, under root of 3, and here is what? 2, so minus 2 plus under root of that term. So that always give you a negative answer. Always give you a negative answer. Same here also, right? Because the zeta value is always greater than this term. So it means this root S1 and S2, there are always negative in case of overdamped system. Okay, so the roots are always being the negative, right? So how to find out the values of the roots and how to find the response in case of overdamped system, that we are going to discuss here. Okay, so in overdamped system, finally we can write the solution of the equation. So we can write here the solution of this differential equation for the overdamped system case. That is what? X is equal to a e raised to, actually e raised to s1t. Just look at the solution, what we have write initially. See, e raised to s1t plus b e raised to s2t. So now we have s1 and s2. So we just put that s1 and s2 in this. Okay, so what we are getting, e raised to, this is my s1 minus zeta plus under root of theta square minus 1 into omega n. This is the s1 into t, because it's a s1t, right? Plus b e raised to minus zeta minus under root of theta square minus 1 into omega n into t. So a1, a e raised to s1t plus b e raised to s2t. This is what the equation of the motion. Now we are going to find out the value of a and b, that are my constants, and it depends on the initial conditions. Okay, but that part is required some time consuming process, so we cannot complete in this 5 minutes that we have left yet. Okay, so first to write this thing. Okay, so write down up to here, later derivation, simplification, and the response part, that we are going to discuss in our next lecture. Okay, so first complete this writing part, and then only gives your attendance in a chat box. None of the student leave. None of the student leave until you have finished this. Until you have finished this. Okay. So complete this and then okay. So if you've done this, then after writing your number, you may leave the session. So this is all about the today's session where we discuss the damped vibration, solution of the damped vibration. We discuss the three different cases: under damped, over damped, and critical damped. And then further part of the derivation and the solution of the equation for these three different cases that we have carried forward to our next lecture. So thank you everyone for attending this session. We'll see you in the next class. Here I can see some students are still in the meeting. Is there any query by any of the student? If not, kindly leave the session as I'm going to end it. Kindly put your attendance. Otherwise, you mark absent.